Let us consider an example. My specifications are this: a fairly practical example. The magnitude is given versus frequency, okay, frequency in kilohertz, not in radians, and the sorry like this, okay, and the tolerance scheme is this in the stop band. Like this. So the pass band tolerance is minus 2 dB. This is 0 dB, and minus 2 dB, and the stop band tolerance is minus 50 dB. Okay, and see, the figure is not to scale. The edges of the pass band are specified as 400 kilohertz and then 1200 kilohertz, and the edges of the stop band are specified as 100 kilohertz and then here 300 kilohertz. Okay, so that's a specification. Right now, actually you don't have to go to omega p1 and omega p2. Okay, you can test with the frequency in kilohertz itself. See here, actually, let me use capital letter F p1 is equal to 400 10 to the 3 hertz, and fp2 passband frequencies, edges of the passband are 1200 10 to the power 3 hertz. So in this case you don't need or you don't have to go to omega p1 and omega p2, because omega p1 is equal to 2 pi times f p1, and this also 2 pi f p2. So no need to calculate this capital omega p1 and capital omega p2. Straight away you can work on it. Okay, see the relation, either you write omega p1 omega p2 is equal to omega naught square, or you can write fp1 fp2 is equal to f naught square, this one or that one, doesn't matter. Okay, so therefore fp1 is given, fp2, and what about fs1? Fs1 is equal to 100 kilohertz 10 to the 3 hertz, and then fs2 is it's 3000 10 to the 3 hertz. Okay, so let us find out fp1 fp2. So this is 400 times 1200, that is 48 times 10 to the how much, 4 4 6 10, okay, hertz. It is not in hertz, it's a number now, or I can say hertz squared. Whereas if you find out fs1 and fs2, this is how much, 100 and 3000, so 3, I can put it 30 times 2 zeros and here 2 zeros, 4 zeros, okay, 10 to the 10 hertz squared. Okay, now if you look at, they are not equal, right? So this FS1 and FS2 is less than FP1 and FP2. In other words, FS1 has to be increased to FS1 prime. Okay, so here the product is less than the stop band edges product is less than the pass band edges product. Okay, FS1 FS2 is less than FP1 and FP2. So I have to increase either FS1 or FS2. If I increase FS2, then my filter will not be a good filter. Okay, I always try to move to the left hand side in the right hand side of the pass band, and in the left hand side of the pass band I always try to move to the right. Therefore let me increase FS1. So FS1 prime is equal to FP1 FP2 divided by FS2. Okay, don't change FS2, only change FS1. So the changed one is FS1 prime. FS1 prime is equal to 48 times 10 to the 10 divided by FS2, how much? 3000, 10 to the 3. So this is how much? 160 kilohertz something. 1 times, yeah, 16, and then 3 zeros plus 3 10 power 6, so yeah, 160 kilohertz. FS1 prime is equal to 160 kilohertz. So initially it was 100 kilohertz. My adjusted frequency will be somewhere here, that is 160 kilohertz. That is my new frequency. Now with these specs you have to design the filter. All right, and the bandwidth is obviously the upper frequency minus the lower frequency. Upper frequency is 1200 minus 400, so this is 800 kilohertz. Now let's find the transformation. Now what is omega naught? Omega naught is square root of omega p1 and omega p2. And you can find out omega p1 is equal to 2 pi capital F p1. So this is 2 pi times 400 times 10 to the 3 radians per second. Similarly, omega p2 is 2 pi times 1200 times 10 to the 3 radians per second. So I don't want omega naught, in fact I need omega naught square. Okay, we need only omega naught square. So omega naught square is equal to omega p1 omega p2. So 2 pi times 400 times 10 to the 3, 2 pi times 1200 times 10 to the 3. So 2 pi 4 pi squared times 4 times 1248 times 20 10 to the 3 10 to the 3 10 to the 8. Okay, so this is my omega naught square. So I have written in this particular form so that I can make simplification. Now what do we require? We require the bandwidth. The bandwidth is in radians per second. So 2 pi times this 800, just now we calculated, right? This 800. So 800 times 10 to the 3. This is 1600 pi 10 to the 3 B radians per second. Okay, so B is in radians per second. We have to express it in radians per second, because the transfer function contains B times omega naught by Q. Therefore, capital S is equal to S squared plus omega naught square, right? Because we know the transformation, capital S is equal to A squared plus omega naught squared divided by BS. So A squared plus instead of omega naught square, you write the value. What is omega naught? Omega naught square. Sorry, this is omega naught squared. 4 pi squared times 48 times 10 to the 10 divided by BS. B is 1600 pi times 10 to the 3 S. So in the transformation, small s must be in radians per second. So you must convert all of them into radians per second or radians per second squared. Okay, so with a little practice you will be able to avoid handling such large numbers. Okay, so I don't want to write the entire large number, so that I have split it into 4 pi square times 48 times 10 to the 10. So the specification by frequency scaling, you could make that into hertz or divided by 100, so that your frequencies are like 1.6 and so on and so forth. I mean, you can handle with a small number, and then the frequency and then do the frequency denormalization. Okay, so this is a transformation from the given low pass filter to band pass filter. So our low pass filter will be like this. It is normalized low pass filter. So 1 radian per second this is, and it's a stop band omega s, and the given specifications are minus 50 dB, and this is minus 2 dB, and this is 0 dB, and this is magnitude. Okay, this value I got it from the given specifications. Now what is omega s? That is the question. Omega s is what? We have to find that out. Find that out from where? What is our baseline? Okay, we can't argue that one is being converted to omega p1 and omega p2. Therefore, I will divide omega s1 omega s2 by omega naught square. No, that will not work. Okay, so generally don't take shortcut. You have to appeal to the basic relationship. What is the basic relationship? The basic relationship is capital S is equal to S squared plus omega naught square divided by BS. So this is the basic relationship and we are trying to find out omega s. So if I put capital S equal to j omega s, then let me call this equation number 1. and then right side of the equation 1 we will have 1 by j omega s1 or omega s2. Okay, the omega s corresponds to omega s1 or omega s2, therefore omega s corresponds to omega s1 or omega s2. The stop band edge of the normalized low pass filter will correspond to the two stop band edges of the denormalized band pass filter. Okay, so capital S equal to a square plus omega naught square divided by j times b omega s1. I put comma here, omega s2. The meaning of comma is or. So the stop band the stop band edge of the normalized low pass filter will correspond to j omega s in the left hand side, therefore j omega s is equal to minus omega s1 square or minus omega s2 squared plus omega naught square divided by jb omega s1 or jb omega s2. Okay, let me say this is 2, and from this relationship omega s will be equal to if you want only the two positive frequencies, then generally omega s1 squared will be less than omega naught squared, isn't it? Therefore we will have to take the numerator as omega naught square minus omega s1 square, and the denominator becomes b omega s1. Okay, so in the numerator I did not consider omega s2, in the denominator also I did not consider omega s2, because I need a positive quantity. If you want a positive quantity, then I need to consider omega s1 square, because this omega s1 square is less than the omega naught square. So this omega naught square has come over here and this one has come over here. So this is the relationship to find out the stop band frequency in the low pass filter. Okay, so this one is the stop band edge frequency of normalized low pass filter, and we know what is omega naught square, omega s1 square we know, and b also we know, omega s1 also we know, so you can simply substitute and you can find out. Okay, so I don't want the negative frequency. See, I did not consider this omega s2 square in this expression. Let me use some other color. I did not consider this y. Similarly, in the denominator also I did not consider this y. If you consider omega s2 in the numerator, omega s2 square in the numerator, and omega s2 in the denominator, then this guy would have been negative. Okay, even if it is negative doesn't matter, because if you take an ideal low pass filter, then the ideal low pass filter would be like this, isn't it? This is let's say omega s minus omega s. So I just wanted the positive, so that's why I have taken this omega s1. So this is slightly confusing, okay, don't get confused. Let me write down one more time. Capital S is equal to a squared plus omega naught squared divided by j times b s. Now if you replace s equal to j times omega s, stop band frequency, see this is the low pass domain, normalized low pass filter, and this right hand side is band pass filter. So on the left hand side, if you replace capital S by j omega s, the stop band frequency, in the right hand side you have to replace this s by either omega s1 or you should write omega s2. Okay, if you take omega s1, then what happens? J omega s is equal to minus omega s1 plus omega naught square divided by j times b times omega s1, or I can write j omega s is equal to minus omega s2 plus omega naught square divided by j times b omega s2. I can use this relation or this relation, but let me call this is a and this is b. Equation a gives me the positive quantity. Why? Because omega s1 is less than omega naught squared. I'm sorry, here also square will come. I'm sorry. What did I do here? Yeah, this here I have written correctly. I forgot to put the square. Okay. So this omega s1 square is less than omega naught square, and here omega s2 squared is greater than omega naught squared. Therefore, this guy gives me the negative value. So that's why I am interested in taking this equation. Okay, so you can take omega s1 or omega s2, but not both. Okay, so now we got omega s of the normalized low pass filter. This we got it, this also we know, and delta p we know, and delta s also we know. And then you can design the low pass filter. Okay, so all I want to know is how should I design this normalized low pass filter. So I need a value of omega s. Whichever way you calculate, you will either find omega s or minus omega s, doesn't matter. Okay, you can't find any other value. Now the positive value of omega s I can obtain in two ways. Either I can take this expression, or I can take this expression. Okay, these two obviously have to be identical. There is no other alternative. They should give the same value of omega s. You can verify that. Okay, if you want, you can do a little more modifications. So what is the first relation? Yeah, take this one, omega s is equal to omega naught square minus omega s1 squared divided by b times omega s1. So this I can write as omega naught square divided by b omega s1 minus omega s1 squared that would be B omega S1. So this is omega naught squared, if you know omega S1, omega S2, right? Therefore this becomes omega S2 divided by B minus omega S1 divided by B. So I can write omega S2 minus omega S1 divided by capital B. So this is omega S. Okay, and see, this omega S corresponds to a normalized low pass filter, and this omega S1 and omega S2 belong to band pass filter. So from the from the given specifications, we will be able to find out this omega S1 and omega S2, because omega S1 and omega S2 are given in these specifications, and B also we can calculate from the given specifications. So with that known value, you will be able to find out omega S. Why omega S is needed? Because our starting point is designing the normalized low pass filter. That's why we are doing this. So therefore the stop band frequency of a normalized low pass filter is the difference between two edge frequencies, omega S2 minus omega S1. And what is the bandwidth? Bandwidth is omega P2 minus omega P1, and the numerator omega S2 minus omega S1. So it is the difference between two edge frequencies. Therefore it is omega S is equal to omega S2 minus omega S1 divided by omega P1 minus omega P2. So we know omega S1, S2, omega S1, omega P1 and omega P2. And this omega S in our case is the normalized analog low pass filter frequency, stop band frequency. So now what is omega S2? Omega S2 is 3000 minus 160 omega S1 divided by 1200 minus 400. Okay, multiplied by 10 to the 3, and here also multiplied by 10 to the 3, but anyway that will cancel. So this is 3.55. Omega is equal to 3.55. So we are now comfortable. Okay, we have to design a low pass filter now. This is 1 radian per second, and this is minus 2 dB, 0 dB, and then this is magnitude, frequency, and this is 3.55 omega S, and this one is minus 50 dB. See, we got the specifications of a normalized low pass filter from the given specification. What is a given specification? The specifications are given for high band pass filter. That's it. Now you can simply work on it. It's not difficult. Okay, so you should be very careful, okay, how to find out this omega S from the band pass filter specifications. We need to find out the stop band frequency of a normalized low pass filter from the specifications, from the given specifications of a band pass filter. So that's a very important point, so you should not make a mistake. So the first thing that I have to do is to convert this minus 2 dB an equivalent to terms of 10 to the minus 2 by 20. Okay, and this should be equal to, if you want a Chebyshev design for example, then this must be equal to 1 divided by square root of 1 plus epsilon squared. And if you solve this, epsilon is equal to 0.765. Okay, I do require epsilon squared also, so therefore this is 0.585. And minus 50 dB in terms of ratio is equivalent to 10 to the minus 50 by 20. So this is 10 to the minus 2.5. And square of it, 10 to the minus 2.5, this is 10 to the minus 5 if you square it. And therefore, in order to find the order, Chebyshev order, instead of using the Cauchy inverse formula, let us use the basic formula. What is the basic formula? 1 divided by 1 plus epsilon square Cn squared of omega s by omega c, and omega c is 1 radians per second. Okay, so this is 1 divided by 1 plus epsilon squared Cn squared of omega s, and this should be less than or equal to 10 to the minus 5 stop band frequency. At stop band, this is attenuation. Okay, with a little practice you will be able to write this without the intermediate steps. So if you simplify this, then this is 1.1 plus 0.585 Cn squared of, what is omega s? Omega s is 3.55 greater than or equal to 10 to the 5. Okay. Divided by 0.585. I forgot this. I'm sorry. I did a mistake. I beg your pardon. Cn squared of 3.55 is greater than or equal to 10 to the 5 minus 1 divided by 0.55. Approximately, I can say 413.45. Okay, so Cn squared of 3.55 is greater than or equal to 413.45. Now let me take n equal to 3. Therefore C3 of x, we know the formula, right? 4x cubed minus 3x. So therefore C3 of 3.55 is equal to 4 times 3.55 cubed minus 3 times 3.55. Okay, even if you take this as 4, then 4 times 4 16, 16 times 4 64, 64 times 4 228. So this is not satisfying. So n equal to 3 will not work out. Therefore n equal to 3 does not suffice. Take n equal to 4. So C4 of x is equal to 8x power 4, x to the power 4 minus 8x squared plus 1. So 8 times 3.55 to the power 4 minus 8, 3.55 squared plus 1. And this is, enough. So capital N equal to 4 is the answer. So NC equal to 4. Fourth order Chebyshev low pass filter will satisfy the specifications on the normalized low pass filter. Now what is the next step? Next step is to write down the low pass filter transfer function as a function of capital S. Okay, so low pass filter as a function of capital S is equal to A squared plus B1 capital S plus C1. Actually C1 multiplied by A squared plus B2 S C2, actually omega p. Okay, this omega p is now 1 radian per second, that's why I did not write down here, and here also omega p will come, but anyway no need to write. And here C1, you bring the denominator constants to the numerator, C1 times C2, and then since it is even order, you should have the multiplication factor of 1 divided by square root of 1 plus epsilon squared. And here C naught is not needed, it is needed only for odd ordered filters. So you calculate yn, here n equal to 4, therefore you calculate y4, okay, and then you calculate C1, C2, B1 and B2, and then substitute all these values in this filter, in this equation, in this transfer function, and get the normalized low pass filters transfer function in the capital S domain. Finally, your band pass transfer function in the small s domain will be obtained by small s is equal to, instead of writing low pass filter, let me write NLP, normalized low pass filter, capital S, substitute capital S equal to A squared plus omega naught squared divided by BS, and that's the end of the design. You know, it's a fairly elaborate process and you can make a mistake at almost every step. Even a very well known, you know, authors have made this mistake. Similarly, you can, okay, so you should be very careful in designing this. Okay, so similarly you can design a band stop filter with arbitrary specifications. So normalized low pass filter is, in normalized low pass filter the transfer function is given in terms of capital S. Okay, then this capital S is replaced by small a squared plus omega naught squared divided by b small s. Similarly, you can design a band stop filter with the arbitrary specifications. Okay, so that's the end of the design of analog filter. Now in the upcoming lectures we will see how to transform the analog filters to a digital filter. Okay, so our next topic would be digital filter structures. Thank you very much.